Monoidal categories and their representations, Lecture 6, Tensor categories and Grothendieck rings. Let us start with the main definition. Let C be a monoidal category and assume that K is an algebraically closed field. Definition. We will call the monoidal category C a tensor category and over our algebraically closed field K, provided that the following conditions are satisfied. First of all, C is supposed to be an abelian category. Then, the category C is supposed to be K-linear and with finite-dimensional morphism spaces. In other words, C is supposed to be enriched over the category of finite-dimensional K vector spaces. The next assumption is that C is rigid. The next assumption is that the tensor product in C is bilinear, so it is K linear in each variable. And finally, we assume that the endomorphism algebra of the identity object in C is isomorphic to K. If we drop the last condition, then we will call C a multitensor category. So a multitensor category is a category which satisfies the first four conditions, and we forget about the fifth one. And a multitensor category C is called indecomposable, provided that it is not equivalent to a non-trivial direct sum of multitensor categories. Here is the prototypical example. Let G be a finite group. Then the category of all finite-dimensional G modules over our field K is a tensor category. Indeed, we know that this category is monoidal with respect to the usual tensor product of G modules. So we take the tensor product inside the category of vector spaces, and if the input consists of G modules, this tensor product has a natural G module structure. Of course, the category of all finite-dimensional G modules is abelian, K-linear, and has finite-dimensional morphism spaces. Also, we know that the tensor product over K is bilinear. The identity object in this monoidal category is the trivial G module K triv. The trivial G module is a one-dimensional K vector space on which G acts trivially, so each element of G acts as the identity map. And clearly that the endomorphism algebra of the trivial G module is just K. So we now have checked almost all the conditions. The only condition which is not checked is that G-mod is rigid. So let us check that the category of finite-dimensional G modules is rigid. And the claim is that this category inherits the rigid structure from the rigid category of all finite-dimensional K vector spaces. So let us recall the rigid structure for the category of vector spaces. The adjunction morphisms for finite-dimensional vector spaces are given as follows. So the dual object for a finite-dimensional vector space V is a dual vector space V dual. So this is a space of all linear maps from V to K. The multiplication adjunction morphism epsilon from V dual tensor V to K is given by the evaluation map. So we take an element F in V dual, we take an element V in V, and we send the pair F tensor V to the evaluation of F at V. So to define the co-multiplication, let us choose some basis, bold V, in our vector space V. Then we have the dual basis V dual in the vector space V dual, and the co-multiplication map eta from K to V tensor V dual is given by the map which sends the element 1 in K to the sum over all I of Vi tensor Vi dual. So this is the description of the rigid structure on the category of all K vector spaces. Now let us see how this gives us a rigid structure on the category of all G modules. First of all, the dual vector space becomes a G module as follows. If we have an element f in V dual and we want to act on it by some g in G, so we get an element gf in V dual, which is defined in the following way. So if we evaluate gf at V, this is equal to f evaluated at G inverse times V. So this should be G inverse. So what we need to check is that our multiplication epsilon and our comultiplication eta, that these two maps, which are just linear maps, we need to check that these two maps actually live in the category of all G modules. So they are homomorphisms of G modules. Okay, let's check it. Here is a computation for epsilon. If we try to apply epsilon to the element G times F tensor V, then by the definition of G, this is epsilon applied to GF tensor GV. By the definition of epsilon, this is GF evaluated at GV. And by the definition of the dual module, this is F evaluated at G inverse applied to GV. So using the associativity of the action, G inverse times G is equal to the identity. This is equal to F applied to V. All this lives in the trivial G module, so this f of v is equal to G times f of v, because the action of G is trivial. And now we use the definition of epsilon and we rewrite f of v as epsilon applied to f tensor V. And this shows that the map epsilon computes with the action of our little g. So this proves that epsilon is a homomorphism of G modules. Now let us do a similar computation for eta. In order to define eta, we have chosen some basis in our V. So let us assume that the action of G in this basis is given by some matrix AJI. Then the matrix of the action of G in the dual basis is given by some matrix Bij, and since this action is given by the inverse of G, so this matrix is inverse to the matrix consisting of AJIs. So now let's do the computation for the linear map eta from K to V tensor V dual. So if we apply G to eta of 1, then by the definition of eta, this is equal to G applied to the sum over I, Vi tensor Vi dual. So now we can use the definition of how G acts on the tensor product, and we get the sum over all I, G applied to Vi, tensor, G applied to Vi dual. We have the explicit matrices which describe the action of G in our basis V and V dual. So using this, we can write this as a sum over all I. So the first factor in the tensor product will be the sum over J AJI times Vj, and the second factor in the tensor product will be the sum over S BIS times Vs dual. Now we rearrange our sum and write it as a double sum over all J and S of the elements Vj tensor Vs dual, and then the coefficient for this element will be the sum over I of AJI times BIS. And now we see here, this is an expression of the element in the product of the matrices AJI and Bij. The fact that the matrices Aij and Bij are inverses to each other allows us to deduce that this is equal to the sum over J of Vj tensor Vj dual. So the coefficient here is 1 if J is equal to S, and is 0 if J is different from S. And by the definition of eta, this is equal to eta of 1. And from the definition of the trivial module, eta of 1 is equal to eta of G times 1, because G times 1 is equal to 1. The action of G on the trivial module is given by the identity map. This completes our computation for eta. Next, let us define the notion of a fusion category. A semisimple tensor category is called a fusion category. And a semisimple multitensor category is called a multi-fusion category. For example, the category of all vector spaces over a field is a fusion category. The second example, the category of all finite dimensional modules over some finite group G, in the case when we work over an algebraically closed field K, whose characteristic does not divide the cardinality of G, this category is a fusion category. And the third example, the category of all AA bimodules, where A is a finite dimensional semi-simple algebra over an algebraically closed field K. This category is a multi-fusion category, and this category is a fusion category if and only if the algebra A is isomorphic to K. The next property which we establish is exactness of tensor product. Proposition: if C is a multi-fusion category, then the tensor product bifunctor is exact in each variable. Proof: we will prove exactness in the right variable, and the proof for the left variable is similar. For a fixed object V in C, consider the endofunctor V tensor with something. So this is the endofunctor of C. We can also then consider the endofunctor V and then the duality on the right, tensor with something. This is another endofunctor of C. The pair V duality on the right and V, so this is an adjoint pair of objects in C. So we have the corresponding adjunction morphisms, and these morphisms give adjunction morphisms between the corresponding endofunctors of tensoring with V and tensoring with V duality on the right. Therefore, the functor of tensoring with V on the left has left adjoint. So this functor is a right adjoint of something, and so it is left exact. Similarly, tensoring with V is left adjoint to tensoring with V and then duality on the left. So tensoring with V is also a left adjoint to something, and so it is right exact. And so tensoring with V is an exact functor, which proves exactness of tensor product in the right variable. Let us consider one more example coming from the theory of Lie algebras. Example: the category of all finite dimensional modules over a complex finite dimensional semi-simple Lie algebra is a fusion category. So let G be a semi-simple finite dimensional Lie algebra over the field C of complex numbers. Consider the category GF mod of all finite dimensional G modules. Directly from the definition, we have that this category is abelian, C-linear, and has finite dimensional morphism spaces. Then the very non-trivial result, which is called Weil's theorem, asserts that this category is also semi-simple. And the next observation is that this category has a natural monoidal structure inherited from the category of vector spaces. If M and N are two G modules, then the tensor product over C of M and N has a natural structure of a G module, which is given by the following formula. If we take an element G in G and apply it to M tensor N, so this is defined as G of M tensor with N plus M tensor G of N. So this defines on the category of all G modules a natural monoidal structure. The identity object is a trivial G module, so it's a one-dimensional G module on which G acts trivially. So any element of G acts as 0. So this module is one-dimensional. In particular, it is simple, and its endomorphism algebra is clearly isomorphic to the algebra of complex numbers. In order to discuss the rigidity property, we need first to define the notion of a dual module. So if we have a finite dimensional G module, then the dual vector space V dual is naturally a left G module via the following formula. So if we take an element G in G and apply it to an element F in V dual, and then we try to evaluate it at a vector V in V, so the outcome is given by minus F evaluated at G of V. And then, similarly as we did for groups, it is easy to check that using all these formulas, the natural adjunction morphisms epsilon from V dual tensor V to C and eta from C to V tensor V dual. So these are adjunction morphisms in the category of vector spaces, that these morphisms are actually homomorphisms of G modules. And this shows that the category of all finite dimensional G modules inherits the rigid structure from the category of finite dimensional vector spaces. And one more property of tensor categories which we discuss is the projectivity of the identity object. We start with the following lemma. If we have a multi-tensor category, then the tensor product of a projective object P in C and any other object X in C is projective. Proof. Let us consider the endofunctors of C given by tensoring with X and with the dual of X on the left. So we put X into the right space of the tensor product. So we have already seen in one of the previous proofs that this is an adjoint pair of functors. So in particular, the homomorphism space in C from P tensor X to Y is isomorphic using this adjunction to the homomorphism space in C from P to Y tensor with X and then duality on the left. So here, if we look at the left-hand side, taking Holmes from P is an exact functor because P is projective, and tensoring with something is an exact functor because tensoring is biexact. So the right-hand side is clearly exact in Y. But this means exactly that the object P tensor X is projective in C, because homing from this object is an exact functor. This lemma has the following consequence. Corollary: if C is a multi-tensor category, then C is multifusion if and only if I is a projective object. So projectivity of the identity object implies semi-simplicity. Proof: so the necessity is obvious. If something is semi-simple, then any object is projective. Sufficiency assumes that I is a projective object. Then, by this lemma, I tensored with any other object is a projective object, which means that any object is projective, and so the category is semi-simple. Great. Let us now discuss the notion of a Grothendieck ring. We start with the setup. Let C be a monoidal category. Assume that the category C is essentially small, additive, and Krull-Schmidt. In particular, it is idempotent split. Assume also that the tensor product is a biadditive bifunctor. Denote by C in bracket and with the sign of direct sum the free Z module with the basis given by the set of the isomorphism classes of indecomposable objects in C. So this assumption of being essentially small is necessary for this in C to be a set. Let bracket denote the multiplicity map. So we start from an object X in C, and the bracket of X will be the list of multiplicities of indecomposable objects in the unique up to isomorphism decomposition of this object in C into indecomposables. Note that this multiplicity map is additive and also surjective by construction. So this allows us to make the following observation. So if we take two elements, X in bracket and Y in bracket, then we define their product as the bracket of X tensor Y. So the fact that our bracket map is surjective says that this is defined for any pair of elements from our set C bracket and then the direct sum sign, and the biadditivity of the tensor product tells us that this defines a bilinear binary operation. Moreover, since tensor product is associative, it also follows that this binary operation is associative. And so our set C bracket and the direct sum sign becomes a ring. So this ring is called the Grothendieck ring of C. This ring is a unital ring where the unit is just the bracket of the identity object in C. So this ring, this free Z module has a distinguished basis, namely the basis given by the indecomposable objects in our category C. And we also know that all structure constants with respect to this distinguished basis are non-negative integers. So if we take the tensor product of two indecomposables, we get an object, and then the multiplicities of other indecomposables in this object are non-negative integers. And a ring with a distinguished basis, with respect to which all structure constants are non-negative integers, is sometimes called a positively based ring. So here is an example. Consider the symmetric group S2 of all permutations of the set 1, 2. And consider the fusion category of all finite-dimensional S2 modules over the complex numbers. We know that there are exactly two simple S2 modules. The trivial module, C-triv, so this is a one-dimensional vector space on which all elements of S2 act as the identity. And we also have the sign module, C-sign. This is a one-dimensional vector space on which the transposition 1, 2 acts as the map minus the identity. The tensor product of these simple modules is given by the following table. So the module C-triv, this is the identity object of our category. The tensor product with this module is the identity. So tensoring C-triv with C-triv gives C-triv. Tensoring the trivial module and the sign module gives the sign module, regardless of the order of the factors. And finally, tensoring the sign module with itself gives the trivial module. This is because minus 1 squared is equal to 1. So this means that the Grothendieck ring of S2, this is a free Z module with a distinguished basis given by two elements. Let's call them V+, so this is for the trivial module, and V- for the sign module. And the multiplication table in the Grothendieck ring is given by the following table. So V+ is the identity element for the multiplication, and V- squared is equal to V+. And then we immediately see that this ring is actually isomorphic to the integral group ring of the group S2 itself. So in this particular case, because S2 is a commutative group, the Grothendieck ring of the category of finite-dimensional modules is actually isomorphic to the integral group ring of the group. Here's example 2. Consider the symmetric group S3 of all permutations of 1, 2, and 3. And consider the fusion category S3 mod, the category of all finite-dimensional S3 modules over the complex numbers. From the representation theory of the symmetric groups, we know that there are exactly three simple S3 modules. The trivial module, which is a one-dimensional vector space on which all elements of S3 act trivially. Then we have the sign module, which is a one-dimensional vector space on which all elements of S3 act via their sign. So even elements act trivially and odd elements act as -1 times the identity. And then we have the two-dimensional simple Specht module, usually denoted as 2,1. And this module is given by the natural action of S3 on the subspace of the natural module. So S3 acts on the three-dimensional complex subspace by permuting the indices of the elements in the standard basis. If in this three-dimensional space we consider the subspace generated by the vectors E1 minus E2 and E1 minus E3, so E1, E2, and E3, this is the standard basis of C3, then this two-dimensional subspace is closed with respect to the action of S3 and is actually a two-dimensional simple S3 module. So here is a table which describes the tensor product of simple S3 modules. It's a nice exercise in the representation theory course to compute this table. The trivial module is, of course, the identity with respect to the tensor product. The sign module squared gives us a trivial module, so this explains row 1, column 1, and this element in row 2. Now the tensor product of the sign module and the Specht module S21 gives us a Specht module S21. This is because this tensor product is a simple module and there is only one two-dimensional simple module. And it doesn't matter what is the order of the factors in this tensor product. The only non-trivial thing to compute here is a tensor product of S21 with itself. And the point is that this tensor product contains a unique canonical copy of the trivial module, and then one can also show that it contains a unique copy of the sign module, which implies that it decomposes as a sum of the trivial, sign, and the Specht module S21. So from this table, we see that the Grothendieck ring of S3 has a distinguished basis, with the elements V plus corresponding to the trivial module, V minus corresponding to the sign module, and W. And the multiplication table in this basis is as follows. So V plus is the identity element. So V minus squared is V plus, similarly as to S2. And then we have this element W, which corresponds to the two-dimensional Specht module. So when you multiply W with V plus or V minus, you get W, but W squared is equal to W plus V plus V minus. And here an interesting observation is that if we take the linear combination of 2W plus V plus V minus, this element is a quasi-idempotent. If we square it, we will get 6 times this element. So this element is a quasi-idempotent with the corresponding scalar equal to 6. And 6 is the cardinality of the group. Another thing which is nice to observe here is that the multiplication is actually commutative. That's a nice feature which we will see appearing in the context of tensor categories later on. And here is example 3, more complicated example of finite-dimensional SL2 modules. So consider the Lie algebra SL2 scheme. So it's a three-dimensional Lie algebra with a natural basis given by the element E, which is the upper triangular matrix, the element F, which is a lower triangular matrix, with non-zero elements equal to 1. And then we have the diagonal matrix H, which has 1 and minus 1 on the diagonal. Consider the category of all finite-dimensional SL2 modules. So this is a fusion category, we saw this, and we know that simple finite-dimensional SL2 modules are in bijection with non-negative integers. So for a non-negative integer n, we denote by Ln the corresponding simple module. So this module has dimension n plus 1, and the action of the basis elements E, F, and H in this module is given by the following picture. So the module Ln has a basis consisting of the vectors Vn, Vn minus 2, Vn minus 4, and so on, all the way down to V minus n. This basis is an eigenbasis for H, so the eigenvalues are just the indices of our vectors. So Vn is an eigenvector for H with eigenvalue n. Vn minus 2 is an eigenvector for H with eigenvalue n minus 2, and so on. The element E acts to the right. So E applied to V minus n is V2 minus n with coefficient 1. E applied to V2 minus n is V4 minus n with coefficient 2, and so on. And the element F acts to the left, also with coefficients 1, 2, and so on, and minus 1. So this is an explicit description of a unique, simple, n plus 1 dimensional SL2 module. So the tensor product of simple finite-dimensional SL2 modules is given by the following formula. If we tensor Lm and Ln, we will get a module which decomposes as follows. So we will get L with the index, the absolute value of m minus n, plus L with the index, the absolute value of m minus n plus 2, and so on, all the way up to L with the index, the absolute value of m plus n. So this means that the Grothendieck ring of this category has a distinguished basis, which is given by the elements vi, where I is a non-negative integer, and the multiplication is given by a similar formula. So Vm times Vn is equal to V with the index, the absolute value of m minus n, plus V, the index, the absolute value of m minus n plus 2, plus and so on, plus V with the index, the absolute value m plus n. And the identity element in this Grothendieck ring is the element V0. The multiplication table in this basis Vi is given as follows. This is, of course, an infinite table, so we show just some finite piece, which is fairly generic. So V0 is the identity element. So V1 squared is V0 plus V2. V1 times V2 is V1 plus V3. V1 times V3 is V2 plus V4. And this doesn't matter in which order we multiply them. So V2 squared is V0 plus V2 plus V4. V2 times V3 is V1 plus V3 plus V5, and so on. We can observe that multiplication is commutative. Also, all structure constants in this basis are either 0 or 1. And also it's nice to point out that if m and n are big, then the number of summons in the decomposition of Vm times Vn in this basis can be also as big as we wish. As a bonus, here is a pictorial description of the combinatorics of tensor products of SL2 modules. I will explain it on one specific example. So let's tensor the simple module L2 and the simple module L3. So using our formula, this decomposes as a direct sum of L5, L3, and L1. And here is the illustration. The simple module L2 has dimension 3, so we take 3 points, and the simple module L3 has dimension 4. We have 4 points. And now we take the product of 3 and 4. So we consider the rectangle with one side having 3 dots and the other side having 4 dots. And now in this rectangle, we take the maximal possible walk from the northwest point to the southeast point. So this walk, we start from this point, so this is 1, 2, 3, 4, 5, 6. It consists of 6 points, so this corresponds to the module L5. So if we erase it, the next maximal walk will consist of 1, 2, 3, 4 points. This is our module L3. If we erase this, then what is left is just 2 points in such a walk, which give us the module L1. So this is a pictorial description of the combinatorics of the tensor product of SL2 modules. We finish with some problems and questions. Question 1. Show that a multi-tensor category C is indecomposable if and only if the algebra CII is a local algebra. Question 2. Check with all details that the category of finite-dimensional modules over a semi-simple finite-dimensional complex Lie algebra G inherits the rigidity structure from the category of vector spaces. Question 3. Compute the Grothendieck ring of the category of finite-dimensional S4 modules over the complex numbers. Question 4. Classify all quasi-idempotents in the Grothendieck ring of this category of S4 modules. Question 5. Classify all quasi-idempotents in the Grothendieck ring of the category of all finite-dimensional SL2 modules. Thank you very much and see you next time.